Hi there, my name is Aaron Lanchman. I'm a professor of electrical and computer engineering at Georgia Tech. In the last couple of lectures, we've looked at integrated circuits we could use to form voltage-controlled amplifiers. In particular, we've looked at operational transconductance amplifiers, and today I would like to look at a specific example of such a circuit, namely the Roland 130 VCA. So for this lecture, I haven't spent a whole lot of time looking at the circuit ahead of time. In addition to talking about voltage-controlled amplifiers, I want to give you a general sense of how I approach a new circuit that I haven't seen before. The Japanese company Roland has always made so many different kinds of music-making products that it's easy to forget that at one point they, in fact, made modular synthesizers. There was the Roland System 700, the Roland System 100M. Oh, and actually, they're making new modular synthesizers in the Eurorack format. And just for fun, let's see how much a Roland 130 VCA, which is the circuit we're going to analyze, goes for nowadays. Well, okay, there you go. And here's our VCA circuit. The signal being processed is coming in on the left, and it's coming out on the right. The control voltage that determines the volume of the signal coming out is coming in over here in the lower left part of the schematic. Interestingly, this circuit gives you the choice between a linear control characteristic and an exponential control characteristic. Now, in that introductory lecture on voltage-controlled amplifiers, I showed you an op-amp circuit that has a voltage to current characteristic that's linear in nature. In a later lecture, we'll look at one that has an exponential characteristic, but I'm going to save that for the discussion about voltage-controlled oscillators. Now, this particular circuit uses BJTs for both the linear characteristic and for the exponential characteristic. This is a little bit complicated, and I don't feel like going into it here. So I'm just going to focus on what the gain from the input to the output is depending on the current going into the control pin of the OTA. But before I do that, let me talk about the mixing structures we have here. So a lot of VCAs would probably just let you plug in one signal, but this VCA conveniently lets you plug in up to 3 different signals. And it mixes those signals with this passive mixing network. Now, as we've seen in an earlier video, passive summing networks can have different problems. Strictly speaking, you'll get different gain characteristics on, say, J1, depending on whether you leave J2 disconnected or whether you take J2 and you connect it to ground. Now, it turns out not to be that big of a deal here. And the reason is that this mixing network doesn't just sum the various signals coming in, it's also heavily attenuating to make sure that the OTA here stays within a reasonably linear range. Just for the moment, let's ignore the volume pots in front here. Basically, imagine that you've turned all of these pots all the way up, so they're not terribly relevant in the circuit. We're assuming that we're driving these inputs with ideal voltage sources, so the 100K resistance of the pot won't really matter if we have these pots turned all the way up. So then I have this resistive divider here. It's not quite obvious, but these input resistors are 180K. And let's see how much attenuation that gives us. Here I've pulled up Octave, which is like an open source rewrite of MATLAB, more or less. So let's see, technically speaking, I would have a 560 ohm resistance in the numerator. Then I would have 180 kilo ohms. So I'm writing E3 here. So that's 10 to the power of 3 plus 560. So yeah, that's a lot of attenuation. Whatever voltage is coming in, you'll only be getting 0.3% out. That's assuming that that volume knob is turned up all the way. Now I could make an approximation and have 560 divided by 180K. And this is legitimate because this 180K is really, really big compared to that 560 ohm. So you get basically the same answer. This is a reasonable approximation to make when whatever error you'll get from the approximation are within the sort of variation you'll get just from the underlying tolerances of the resistors you're using. Now, I have made another assumption besides assuming that our volume pots are turned all the way up. I've assumed that we don't have anything connected to the inputs here. We would get a slight variation if we were to ground, say, one of these inputs, because now we don't just have 560. We would have 560 in parallel with this 100K to this ground. However, 560 ohm in parallel with 180K, that's going to be really, really, really close to 560. It's just going to be barely below it. So an effect that we get from having this shunt resistance being so small is that whether you plug other inputs into here or not doesn't really change the gain characteristics very much. And in fact, there's companies that will sell you very expensive boxes that are not really anything more than some jacks and some resistors. And these are called passive summing boxes. And they'll put these shunt resistors in the network to try to eliminate some of those weird effects you get when you connect or disconnect various inputs. But this does also have the effect of attenuating your signal a great deal. And so they'll say that, well, you take your output of your summing box and you could run it through something like a Neve microphone preamplifier that will give your mix all sorts of warmth or whatever. I don't know. It just seems strange to me to drastically attenuate a signal just to then boost the gain back up because maybe you're introducing noise. I don't know. A lot of people like it, and they've produced Grammy-winning records that have sold billions of copies, and I haven't, so what do I know? If it makes them happy, fine. Now, if you really wanted to do a detailed analysis, you would want to include the effects of this pot. So let's say you had the pot turned such that one branch was 50K and the other branch was also 50K. Well, then you would have a voltage divider where the denominator would have 50K plus this 560 ohm plus 180K then in parallel with this 50K on the lower branch. And if you really wanted to handle that in detail, you would also want to consider the effects of these other inputs at different settings. But I'll tell you, in real life, nobody actually does that. You would never worry about it at that level of detail. You would pick some values that you think would give you the basic attenuation that you want and go with it. Now, we can contrast that with the control voltage mixing network down here, which is using active mixing. So this op-amp here, this 4558, is holding this node here at a virtual ground. Now, you're probably wondering what that 15K resistor is doing there. And if this was an ideal op-amp, you wouldn't need that 15K there. But the 4558 has BJT inputs. It doesn't have the super, super high input impedance that you would get with JFET or MOSFET inputs. And what this resistor is basically doing is compensating for some of those non-ideal effects. So just know that that's there. For the purposes of this course, we won't worry about getting into that in more detail. This is a pretty standard thing you can find in books about op-amps and on manufacturers' application notes. Unless I distinctly tell you otherwise, I'm always going to treat op-amps as ideal. So because we have a low impedance summing node here, these various inputs are essentially decoupled. I don't get weird effects such as the input impedance seen at J1, changing depending on what's happening at J2, etc., etc. If you did want to think about what the impedance was, it would be whatever the impedance of the upper branch of the pot is, plus whatever the impedance of the lower branch is in parallel with this 100K input resistor. It would be interesting to make a plot of how that input impedance changed as you sweep the knob, but I won't worry about that here. Notice that one of the inputs we have here isn't actually an input, it's just a knob that's going from whatever the positive supply voltage that they're using is to ground. That way you can set a general volume without having to actually plug anything into one of the inputs, and that would be fairly typical. Notice they're using a different resistor here. This is 150K instead of 100K, so they've made some choices in having this scale things differently. And I'm going to guess these differences are probably something that they chose experimentally. And so if you're wondering about this trim pot up here, especially because it's going into this 1 mega ohm resistor, forming kind of a big voltage divider with this 560 ohm resistor, this is basically here to deal with non-ideal characteristics in this real OTA. So this is putting a very, 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 very tiny voltage here that one can use to adjust for these non-ideal effects. Probably somebody at the factory has voltmeters attached to various points, and then they adjust this to try to make sure that the output here is 0 when the input is 0. As usual for my analysis here, I'm going to assume our OTA is ideal, so I'm just going to pretend that this sort of stuff isn't here and treat this input as if it's grounded. Okay, so what about this BA662? So this was a custom OTA produced by Roland. Roland was a large enough company that they could have their own custom chips manufactured. Let's see if we can find a datasheet. Okay, so I wasn't able to find a datasheet, but I found that the Most Amazing AM Synths website had quite a bit of information about it. It's not a DIP, it's a SIP. It's a single inline package instead of a dual inline package. And if I scroll down a little bit, here's a pinout. So it looks like pin 2 is the negative input and pin 3 is the positive input for the voltage inputs. So up here we have the negative input, and down here we have the positive input. That's a good thing to keep track of. I'm going to assume that otherwise it has the same characteristics as something like a CA3080 or an LM13700 or something like that. So what's going on here? This is a JFET acting as a voltage buffer. This is essentially equivalent to this thing we do all the time where we take a op-amp and take its negative input and tie it to the output, and then plug a voltage into the positive terminal. You don't actually have to worry about the 10K resistor there. That's a typical value we stick there to make the JFET do its buffering goodness. Now, if you've looked at FET transistors at all, you probably haven't been looking at JFETs. You've probably mostly seen their MOSFET cousins, which are very, very useful for, say, building digital computers. But don't worry about that level of detail. All you need to know here is that this forms a source follower that acts as a voltage buffer. The gate of the JFET provides a very, 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 very high input impedance. So it basically separates this part of the circuit over here from this part of the circuit over here. So let's see what the gain is if we look at the high output based on whatever the current flowing into the control pin is. And I'm going to call this IABC because that's how it's usually labeled on the datasheet, the amplifier bias current. I'll also sometimes call this I subscript CON for control. For this next bit of analysis, let me suppose that this capacitor isn't in the circuit. I'm just going to focus on this 33K resistor here, and then we'll talk about the capacitor later. All right, so let's go back to Octave. We have this attenuation factor of 0.003 something. I'm just going to truncate it there, times whatever the transconductance gain of the OTA is. So that's going to be 19.2 times this control current, or what did I call it? I said IABC. So that's our control current. So just keep track of the fact that there's this control current number sitting there in your head, and we'll put it back then later. Now we need to turn it back into a voltage. That's what the 33K resistor does. So it's all of these numbers times whatever the control current is. So let me just go ahead and compute that. So I'm getting 1900.8. Let's see, what does it look like if I actually put in the more detailed numbers that I had above? It does look different. What if I did something like this? So depending on how you interpret the input divider here, you do get some different numbers here. They're all 19 something something though, so you're getting something between 1900 and 2000. Fortunately, humans are not very picky in terms of determining small changes in volume. Remember, the actual gain is going to be this 19 something something times what the control current is. So it would be useful to know what the actual maximum current generated by the circuitry is to be able to know what the maximum gain through the circuit is. So I don't feel like trying to analyze this mess in a whole lot of detail, but here's my hypothesis. Based on other patterns I've seen, let's take, I think, the most accurate of these calculations we did, which would be this 0.00311015. Let's say that the maximum current generated was 0.5 milliamps, or equivalently, I could say 00, not 5, because that would be 5 milliamps. I went 0.5 milliamps. So that's nearly 1. So I just want to point out that if this circuitry down here creates 0.5 milliamps, which is sort of a nice number, then you get unity gain or something close enough to unity gain through this VCA. I'll probably guess that that is what you would get if you have this knob turned all the way up. But again, that's just a hypothesis. We would have to analyze this in a lot more detail to figure out whether my hypothesis is right or not. I should note that most OTAs suggest that a good practical maximum for the input current is something like 1 milliamp. If you start pushing it beyond that, then you're into iffy territory, and you might fry your OTA. But that maximum will vary from OTA to OTA. You'll want to check the datasheet. An interesting feature of the output is that it offers this attenuator. You could take the output here directly, and that's going through this 1K output impedance, and that's there for some short circuit protection. Or you can take it through this voltage divider if you wanted an attenuated version of the output for some reason. And let's see how much attenuation we get from that. So technically speaking, you would be dividing over the 3.3K resistance. So I'll write 33 plus 3.3. Notice I'm not bothering to add E3, E3, and E3 to everything since all of the Ks cancel. And so we get 0.090909. That's pretty close to 0.1. So if we make this R small plus R big is equal to R big approximation, then we would wind up with 0.1. So the low output gives you around 10% of what the high output would be, if for some reason you wanted that. So the last thing I want to do here is talk about these capacitors. There's some that I've basically ignored entirely, and that's this 10 microfarad 25 volt cap and this 10 microfarad 25 volt cap at the input and output. These are just DC blocking capacitors that block any DC offsets in the signal. And you can tell that because they're very high capacitances for audio. Notice that you don't actually see a microfarad written here, but in the kind of circuits we're looking at, if they don't write a unit for capacitance, you can assume it's microfarads. If it's something else, they'll indicate that. So I'm not going to bother analyzing the effect of those. I've been implicitly assuming that those were short circuits the whole time as far as our analysis is concerned. Let's check out this 47 picofarad capacitor. So before we do any detailed analysis, let's just think about what it is at the extremes. So at low frequencies, we can approximate the capacitor as an open circuit. So this is basically the assumed circuit that we've been analyzing. Well, what about at high frequencies? As you get to very high frequencies, this will start to look like a short circuit, and the output here is getting shorted to ground. So whatever current coming out of here doesn't really matter because the output is effectively shorted to ground and you don't get anything out. So before we do any kind of algebra or anything, we know that this capacitor will have a low-pass filtering kind of effect. So this is going to form a one-pole filter, but instead of a voltage in, voltage out filter, this is an impedance, so we can think about it as turning a current into a voltage. And essentially we have the same analysis, except instead of a 33K resistance here, we have a more complicated impedance. At DC, all of the results that I've computed previously still hold. So we can basically pile the frequency-dependent effect on top of that. At DC, we could use this gain formula of 1965.1 times IABC. And on top of that, we can pile a one-pole low-pass effect. Now, the cutoff frequency for that in terms of radians per second would be 1 over the time constant associated with this resistance and capacitance. Our R is 33K, and our C is 47 pico, so that's 47 times 10 to the minus 12. Here's 1 over RC. And now let's take that omega C and divide it by 2 pi to get our half power cutoff in hertz. And that's 100K. So that's well above the range of human hearing. So I'm going to guess that maybe they were having some sort of stability issues where they had some sort of parasitic oscillations of some kind somewhere that they were trying to get rid of, or maybe some other high frequency noise source. And that's why they put this capacitor in there to get rid of that. Anyway, it doesn't have a musical effect. Although another thing I might worry about on this schematic is maybe there's supposed to be a dot between the 4 and the 7, in which case this would actually be 4.7 picofarad. So let's see how that changes if we change this to 4.7. Okay, that's even higher, right? That would be about a megahertz. I bet that's 47 pico and not 4.7. In any case, it doesn't really change our analysis of what's happening musically. Let's see. The other capacitor I'm interested in is this one down here. This is providing a low-pass filtering effect on the control voltages that are being mixed. And let's go calculate what the cutoff is for that. So omega C would be 1 over 0.01 microfarad. Again, capacitances in these kinds of circuits are always microfarads unless they say otherwise, times 68 E3, 68K. And now let me take that and divide it by 2 pi. So that gives us 234 hertz. So if you think about that from the standpoint of audio frequencies, that's a pretty low cutoff. But remember, this is intended for control voltages, and at least in this modular, they're not expecting those control voltages to vary terribly quickly. So the last thing I want to do here is to fade to black and justify my 1 over RC formula for the half power cutoff point. Now, what we had was we had a resistor in parallel with a capacitor. So the impedance of this would look like R times the impedance of the capacitor, which is 1 over SC, divided by R plus 1 over SC. Let me divide the numerator and the denominator by R. So I'll have a 1 over R up here and a 1 over R down here. And let me also multiply the numerator and the denominator by S. So let me write it like that. So I could rewrite this as R times 1 over RC over S plus 1 over RC. And now that's just R times omega C over S plus omega C. So that's just using my definition, omega C equals 1 over RC. And if we plug in j omega for S to get a frequency response, you can see that if I then plug in 0 for omega, I'll have omega C over omega C, everything cancels, and that gives me R. So I just get that resistance back at DC, and that matches with our intuition that at low frequencies, capacitors look like open circuits. Similarly, if I instead decide to let omega go to infinity and see what happens at high frequencies, these constants essentially get swamped. I have the reciprocal of something going to infinity, so it goes to 0 and it has a filter effect, which is what you would expect at high frequencies because this looks like a short. And I'm not going to go through the details here, But if you take this quantity where you plug in J omega to get a frequency response, let me use capital H for my frequency response, you'll see that if you plug in omega C for omega, the magnitude squared of this is equal to 1/2, which justifies calling it the half power point.